check out the transistor. What I explain both are NPN, then it will happen, the current will come out easily. But in case of PNP transistor, we will know that thing will be opposite. Once it will be on, then it will be supply a current, or it will hold a voltage, which will be zero due to conduction of the current, and later on it will give you minus VCC, that voltage across resistance. So in the next half cycle, when it will be minus, I will find here a next voltage is the minus. Okay. So this way we will create a positive half and negative half, and this is called push-pull arrangement. Okay. So what I am going to mean, now come to that point. This is basic diagram of op-amp amplifier. The first one we discussed. Second is intermediate state. This is also difference amplifier, but dual input, unbalanced output. The output was unbalanced, and earlier the dual input balance output is a very good one. That was the first transistor. We consider similar second stage of transistor. Third one is the emitter follower, that actually biasing systems which reduce the noise and uniformly pass out the input voltage to the output stage, and there will be push-pull systems. And finally, we will get the output. So finally, we will get the output. This is the whole block diagram of operational amplifier. Now, if we jump back to your earlier circuit, this one is a my transistors operational amplifier, and this is equivalent circuit. We usually drawn this way. All the amplifier has said here what input impedance is so high, it's like that stage ZF. Normally the op-amp have a certain kind of specification. Its input impedance is high. Means input impedance, resistance and capacitance and inductance. But you will not find inductance here. There will be small capacitance effect. So that's why I am calling it a input impedance, not input resistance. Still, the input impedance of the op-amp is high. Why it is high? Are you listening now? Are you listening?
Yes, sir.
Yes, sir.
Why it is high? As you have drawn a picture of the operational amplifier, that is a differential amplifier, where inverting input and non-inverting input given this way. And what was the circuit? This was our circuit. So look here. If we consider this is inverting terminal, and this is non-inverting terminal. Okay, and output voltage V out. From this circuit, V output voltage definitely IL into RL. RL is a resistance. Any doubt? The output will be IL into RL. Any doubt? Do you have?
No, sir. No, sir.
Awesome. Now, the IL depend on what? IL depend on IC1 and IC2. Okay, IC1 dash and IC2 dash. Look, IC1 dash, IC2 dash. This is the general expressions of IL. Now you put here, so you will find this will be beta IC1 dash minus IC2 dash into RL. Right? I just replace the IL by this expression. Nothing more. What I will find here, that what we'll find there, that if V1 is greater than or V2, V1 is greater than V2, then what happened? IC1 definitely will be greater than our IC2. Okay, IC1 greater than IC2. If V1 greater than or V2, then definitely IC1 greater than IC2 dash. So the value here, V output will be positive. That means that V1 will be whatever the polarity of V1, output voltage will be same polarity. Am I right? As
Yes, sir.
V1 is the reduction of V2, so output voltage also positive here. So whatever the polarity of this one will be, output voltage will be same. So this will be non-inverting terminal. Then what will be that? If V2 greater than V1, definitely
Polarity opposite.
thing will be opposite. So IC2 will be greater than of IC1, but expression remains same. IC1 minus IC1 dash minus IC2 dash. So the output voltage will have a negative polarity. So look here, V2 might be positive value, positive voltage, but output is here negative. So this is then non-inverting terminal. This is then non-inverting terminal. Is it clear? This is a first one, or this is first one. What you learned here?
Sir, could you explain the V1 greater than V2 case once again?
Which one? This one.
Sir, V1 greater than V2, sir.
If V1 greater than V2, then my expression was V output is IC1 minus
IC2.
IC2.
IC2. That's why if V1 greater than IC1 will be greater than beta will remain same. If V1 greater
Yes,
than, then IB will be greater. IB is what is IB? What is IB?
Beta IC1.
What is IB?
IB is beta IC.
No. How can you derive IB from here? Base circuit. Yesterday I told you that, or last day I told you that IC actually, how you have to calculate? You have to calculate applying Kirchhoff voltage law. This is V input. This is V input. So if Kirchhoff's voltage law, if you apply here, this is V input, and there will be voltage VB, and there is a voltage IRE. and this is minus V. Minus V plus V plus VB plus IERE. Okay, by what? The current flowing through this one. What is? By internal resistance by R. R means resistance of this one and plus RE. So the VRE plus RE. This is the total resistance here. Total voltage by
Yes,
total
sir.
resistance. That will be the current. So this is IN. Now you will see here V in increasing. V in increasing means current is increasing. Okay. So the
Yes, sir.
total voltage, if you think out of this one, then the some X voltage, which actually minus V plus VB plus IE RE and a RX, which is RE. Then the current IB will be Vx plus V by what? By RB and sorry, this is called RB. So this is RX. If I going to make it simple way, VE, that voltage is fixed voltage, right? Right, fixed voltage. Now
So
current
VE
through
means V in minus VEE.
what?
Sir, VE, sir, what does that mean, sir? It means V in minus VEE.
VE minus.
So there
No,
is
I'm
V.
considering that in Kirchhoff's law there will be a voltage drop. Let me make it clear.
Yes, sir.
If we
Okay, sir, I
make
got it, sir. I got it.
if I am going to make a circuit like this one, this is V in, this is VB, this is IE, RE, and this is minus VE. Is it visible now? If I am going to make equivalent circuit of this one, it is like that. Look here, as I told, this is input voltage. This is input voltage, and this is VB, that conduction voltage. This is RE. You connected through what? IE, RE will flow. When it will flow IE, RE, your transistor will be switched on condition. Otherwise, it will not conduct. No? Transistor required to be switched on, then there will be current IE, RE. That IE,
Yes, sir.
RE will come this way, and there will be V minus. Now, the total voltage is this voltage plus this voltage plus this voltage plus this voltage. This part, it will make you little bit confused. So you make it a straight line. Remove the resistance. If you remove the resistance, that will be common emitter circuit. Okay, no issue. You just remove the resistance. Then this part will be simple to understand. I have connected. So that VB plus V plus minus VEE will be my total voltage. And what about the resistance? What about the resistance? Resistance mean now it is a simple resistance as I have ignored that resistance. So there is a resistance of the reverse bias, and this is fixed Rx. Then the current IB base current at base will be total voltage by equivalent resistance. Am I right? I have written RA means the source volt may have some resistance. So I said the term is equivalent resistance. I have to consider the source resistance as well as the resistance between base and emitter of the transistor. Okay, and the emitter resistance RE I have considered it is zero. I mean zero means it is conducted by it is short circuited. So I remove the resistance. So there is no resistance RE. So only the resistance of the source D and resistance of the base and resistor and resistance of the minus V. That is I consider as equivalent resistance Rx. So the IV base current will be total voltage across Kirchhoff's law by total resistance of the circuit. That is IV. Now you think that if if V1 is increasing, V1 is both are those are remain same. Those are remain same. You are not able to change them because according to the transistor they remain same. What you can do if you increase V, then IV will increase. Similarly in V2, if we increase V2, then you will find that IV2 will be increased. Okay. Is it?
Yes, sir. Yes, sir.
Yes, sir.
Now I am going to consider the expression of voltage. Voltage, what I consider? It will be voltage due to that transistor minus voltage due to that transistor. Okay, that is the output voltage. So voltage due to that transistor is greater, then the output voltage will be positive. If voltage of this transistor is greater, then output voltage will be negative. Am I right?
Yes, sir.
Yes, sir.
So polarity, if you consider the polarity, the V2 terminal is when is dominating. Whatever the voltage, V2 terminal is dominating, then V1 terminal, definitely the output voltage
Inverted.
is opposite direction, opposite in polarity. Eh? Definitely output will be opposite in polarity. So when voltage
So basically, the sign, let's say V2 sign is equal to the sign of the output. So the V2 is the non-inverting terminal and V1 is the inverting terminal in that case.
that's the point I am to say. If you say yes, I can move on.
Yes,
That
sir.
means here that you understand this one. Okay, this is
So
the important part. Definitely, it will be discussed in electronic circuit theory. But a electronic circuit is an important part of the transducer for signal conditioning one. As you have not understood it earlier, so I am make it clear. I am going to make it clear in future whenever I am going to say signal conditioning part. You just remember there will be transistors or there will be op-amp which actually amplify the signal or attenuate the signal as well as filter the signal. These are the important actually operation or function of the signal conditioning element or intermediate modifying elements that I started in discussions. So you find here inverting terminal, non-inverting terminal. This was the inverting terminal or non-inverting terminal of a op-amp. It's actually op-amp of a actually studied. So this was our op-amp. First we consider this was your op-amp. And as you have seen that there is a two transistor having input V1 and V2. Both inputs are where? In base. Am I right?
yes, sir.
Baba, তোমরা শুনতে পাচ্ছ তো? They are connected in base of the transistor তো। And we
Yes,
know
sir.
there will be reverse bias region. So the reverse bias region, what is the stage value of resistance in reverse bias? Collector base will be reverse bias. Am I right or wrong? Of an NPN transistor.
Yes, sir.
So if you think that is a reverse bias, then the value of the resistance in reverse bias is in mega ohm in order. Okay, mega ohm in order. So that's mean high input impedance. High input impedance. So we are considering two terminal here. We are considering two terminal here, and all the terminal actually connected to a high impedance resistance. So what I can say, the op-amp has high input
Impedance.
impedance, or sometimes it is called infinite impedance. So op-amp has high input impedance or infinite impedance if it is ideal op-amp. In practical op-amp, it will be mega ohm in order. Okay. What about the output impedance? Whatever the output impedance, that is very low because most
So
of the current
ideal is
passes to
zero.
the, okay, most of the current will force to pass through the resistance. The resistance is itself, resistance means what? Resistance is here R, and
Sir,
most of
which
the
one
current
is reverse bias, sir?
huh?
Base
Sir,
collector.
which part was reverse biased, sir?
Which one is reverse bias? Tell me. You tell me.
So the
You
input
started
is supposed to
the
be reverse biased.
huh?
So the input is supposed to be reverse biased.
N P N. This is P. This is N. This is N. Now, which one is the reverse bias?
So the collector base junction is reverse bias.
Sudhasatta.
Yes, sir. The NP part is reverse biased, sir.
So, NP part means which one? The collector base or base emitter?
Collector base, sir.
That's why we consider is the VBE. VBE means diode forward voltage. If we're going to draw the diode current and voltage diagram, it's forward bias, this is forward bias, this is reverse bias. Diode current used to be like that. Am I right? In case
Yes,
of
sir.
Zener diode, this will be minus 5
Yes, sir.
volt. So this is actually diode forward bias voltage or threshold voltage. Sometimes it is called VT. In case of transistor, is they connected in a forward bias, then that VT will be equal to VB, which is 0.7 for silicon or 0.3 for germanium.
Germany.
Okay,
Excellent.
so this one is a forward bias and this one is the reverse bias. Any doubt?
No, sir.
Sudhasatta?
Sir, I got it, sir.
Now, you may a little bit confused as I told earlier that in a KVL loop we will apply in the base structure that there will be resistance due to reverse. Am I right? Due to what you might be confused. Just hold on. Hello. Hello. Uh-huh. হ্যাঁ আমি পাঠিয়েছি, প্রবেশিকে পাঠিয়েছি তোমার এই জন্য তো কোর্স কমপ্লিশন সার্টিফিকেটের জন্য আমি প্রবেশিকে পাঠিয়ে দিয়েছি এবং ফরওয়ার্ড করে দিয়েছি কন্ট্রোলের সঙ্গে। So I think you may do one thing more. You come to university as well as you directly contact with controller. If you have a certain kind of idea, হ্যাঁ আতিকুর রহমানের সঙ্গে আমার কথা বলে যাবো। হ্যাঁ তোমার যদি আন্টি থাকে উনি যদি আমাকে পাঠাতে প্রিন্ট করে দেন। So, as you may be confused that earlier I have considered that when we are going to apply KVL, there will be some resistance across transistors. So that might be resistance, as I said, resistance of forward bus and reverse bus. That resistance due to not only reverse bus, resistance due to forward bus and reverse bus. There will be certain increase of resistance when we are going to do the stability configuration of the circuits, and that stability is required due to what the reverse bus regions. That's why in total or mostly I said the resistance of the circuit. I don't need to discuss the whole op-amp circuit details. Otherwise, I cannot complete my syllabus. This is fundamental of instrumentation. When you will study analog electronics, you will find there will be some vision of thermal runway. That's why there will be some part of resistance actually connected such way that the current should be fed back to the input side. And this is happened due to the thermal runway due to happen what? The reverse bus between collector and base region. Reverse bus of collector and base region. The resistance is high there, so the heat will be I square RT. So due to small current, the heat will be enough to burn out the semiconductor. Okay, that's why some resistance will be fed to the input sides, connected to the input side, and also there will be part of resistance in base side. So the total resistance of the base side is Rx. I said that is equivalent resistance, not only region of the resistance presence in the input internal source, also the resistance due to reverse bias as well as forward bias of the transistors. Okay, I have not said in details how that resistance will be fed or will be considered in the input side. That should be discussed in details when you will study the analog electronics circuits. Okay, now this point is here. I understand that why it is called inverting terminal and why it is non-inverting terminal, how the op-amp output is related with these two terminals. Okay, and one important thing we learned here, the input impedance of the op-amp is very high. Why it is discussed here, because you will find that the voltage whatever we are giving as input, okay, that terminal and that terminal is behave like a ground, because once we connect a resistance circuit here, the current entering will find that this is the highest impedance part and this is the lowest impedance part. Then what happened? The most of the current follow which one?
The low
Lowest
impedance part.
impedance part, right? The most of current will follow lowest impedance part. Then we will find there is a no current here passing through the resistance. So the voltage across this one will be zero. Similarly, voltage here will be zero. And this is called, that's why, virtual ground. That's why called virtual ground. Which one is an important term in op-amp? Which was an important term in op-amp? Okay.
Yes, sir.
What I said the term?
Virtual ground, sir.
Which point actually create a virtual ground?
V2.
V2 terminal.
Why it is happened? This loop. No input inverting, not an input at the inverting terminal. It's not non-inverting terminal. Normally non-inverting terminal will be ground. You look over that picture, you will understand. Look this part. That circuit. This circuit is connected here. This is connected here. Okay. So look, this is ground, real ground. This is real ground. So this is connected here means it is a real ground. Real ground. And this is negative, and what happened here, the input impedance is high. As input impedance high, then no current try to pass through this one. So it's behave like that. It's a ground, zero. But is it really connected to the ground? This one?
No, sir. No, sir.
Directly, no. So what happened? It's also zero voltage due to this one zero voltage, and it is called virtual ground.
Virtual ground.
This one. Here it is written virtual arc at summing point. Virtual arc at summing point. If it is not grounded, if it is not grounded, suppose there will be small voltage, small voltage you connect here, suppose 1 millivolt, then you will find that 1 millivolt here, and this is resistance. So here will be similar like a 1 millivolt. So that two voltage, I mean the voltage difference between this terminal after the summing point, between this terminal, VD is 0. VD is 0. After the summing point, the voltage difference between V1 and V2, that is VD, is 0. So if V1 is grounded, then V2 will be grounded, and V2 will be called virtual ground. If V1 having a small voltage, very small voltage, even 1 millivolt, that is called bias voltage. That is called bias voltage, or due to the minority current, minority voltage. VCO you have studied in transistor, na? VCO or ICO. In case of transistor, you have studied that is VC plus VCO, IC and I plus ICO. What is ICO? What is VCO? In transistor, that is a very small current or small voltage created due to the magnetic carrier force. Okay. You must study two author actually famous terms, famous common name actually Chattopadhyay Rokhi of basic electronics. Have you studied that Chattopadhyay Rokhi of basic electronics?
No, sir. We studied the Newman and
No,
Street.
sir.
Millman Halkis. So
Yes, sir.
you may study Millman Halkis to understand the op-amp also, or ceiling below. Or Chattopadhyay Rokhi to understand the op-amp, basic op-amp. 2 or 3 pages you must study. You must study 2 or 3 pages. You can even download that part from internet. But the studying book is always best, because there will be few words in a book specially mentioned, which is kind of special knowledge, and it force you to think about the details of the subject. But when you are studying some material downloaded from internet, might have no that kind of the informations. So you always to be you must bend to the study the textbook. These are the authentic, as well as will give you the good information or special information about the electronics one or whatever else, about the which one you are studying, for what you are studying. You must study the textbook or reference book, not the internet and all. Internet sometimes give you the information, but that information is not authenticate. Even some special information will be missing, because that internet information is truncated or copied, or some kind of modified copied version of the some textbook. So these are not in details. These are also not help you to think something new. Whereas you may read that one and to get some number, but definitely the internet information will not help you to think something more. What I am going to say here, that virtual ground you know, and finally you will find that there will be difference. Now this is the basic circuit of inverting amplifier. Earlier circuit, what I have shown you, that is a open loop circuit. Huh? That is actually open loop circuit. This is open loop circuit. I mean, why it is open loop circuit? Because you will not find any connection between input and output. Any connection between input and output. Why it is open loop?
No connection between input and output.
No connection between input output. So that means whatever the voltage difference means V1 minus V2, that is differential voltage D, VD, VD, that will be considered as the input voltage. That will be considered as the input voltage. And what about the output voltage? The output voltage V output always gain, open loop gain into V differential voltage. Now what is open loop voltage? Normally the IC's popular one is 741, and that op amp have a gain is 10 to the power 6. 10 to the power 6. How that op amp used to look? How it look? Let me show you some pictures. This is the IC 741, the first IC in your life you are going to study. In future, you in 4 years you may study more than a 10 or 20 number of IC, but this is the first IC you are going to study. What 741? What is what I said? The IC number is
741.
What is the IC number? What is the diode number normally used in case of basic electronics? IN0007. Similarly, here that op amp will have a general IC number, that is 741. Some op amp are there also with the defined IC number. The number of op amp will be defined there. It is made of particular family of IC. Anyhow, this is this diagram diagram is known to you, and as well as this is the commercial available IC. You will find it is a 8-leg IC. It is 8-leg IC. These 8 legs are given this here. The first one is the offset nullification. Second one is the negative inverting, inverting terminal. Third one is the non-inverting terminal. Fourth one is minus B. This one is the minus B. And eighth terminal is no connection. Seventh terminal is VCC. Means this one. And that is sixth terminal, actually output terminal. This one output terminal. And fifth terminal is offset nullifier. There is the two terms 5 and 1 will be offset nullifier, and 2, 3 is the inverting non-inverting terminal, and 8 is the output terminal. 8 is the 6 is the output terminal, and VCC and VE, that two terminal is 7 and 4. This is the IC normally we have to connect, and whenever you are connect, you have to keep this notch. This here you will find a notch. You will find here notch. A simple, a small bend or small bend. Can you see this one?
Yes, sir.
You will find a bend, a small hole. That is called notch. Notch. That notch should be left hand side, and you are according to what you have to put this one IC on the breadboard to make a connection like amplifier or non-amplifier, whatever. So these are my terminal I discussed. Now I am going to discuss this one. So this is inverting amplifier, and earlier is the open low amplifier. Open low amplifier, the output voltage. What I consider output voltage. Open loop gain. Sorry. The output voltage.
Open gain into VD.
VD. Okay. And these are not fed, the output is not connected to the input. Now in case of closed loop connection, this is called closed loop connection. And closed loop connection, we will find there is a resistance between presence between input terminal and output terminal. And there are also resistance after before the voltage input. Okay, that is particular summing point. That is called summing point or node. So according to Kirchhoff's voltage law, what you can find here? If you apply Kirchhoff's voltage law, the current law, why you can apply Kirchhoff's current law? Do you have any idea of Kirchhoff's current law? Boys, girls?
Yes, sir. Yes, sir.
Sir, at the node
Sir,
X,
at the
we can
summing
apply.
point, yes.
So this is a node, and there is another node is here. We cannot connect Kirchhoff's current law here because there will be certain portions while low impedance part, as I told. So if we apply the Kirchhoff's current law here, then we have to consider a part of current will be fed inside the op-amp, because low impedance path at output terminal, but this part we cannot measure. So that's why we cannot apply Kirchhoff's current law here. We will apply Kirchhoff's current law here. Okay. Now once we connected this one, we will find that output voltage V0, input voltage here. Suppose we just consider the V2. V2 is here. Although V2 and V1 will be same, and VD is 0. Right?
Yes, sir.
So V1 is 0, then V2 is 0.
Yes, sir. Virtual earth.
So virtual ground, this is 0 volt, and this is input voltage V1 volt. Now that current here will enter this way, V0 minus 0 by what? RF. This is the current, output current, and there is the input current IN. IN, oh, what is IN? Input current. VU1, definitely high voltage, and this is 0. So current from high to low by R. Okay.
Yes, sir.
So the current here. So the current here. Current here. V in minus 0 by R in, or V in by R in. So this is current entering, this is current entering, and this is 0. That's mean the sum of entering current equal to sum of leaving current, right?
Yes, sir. I0 equals.
Huh? What is Kirchhoff's current law?
Yes, sir. So I0 will be minus of IN.
So we can say V in by R in plus V0 by R is equal to 0, right? Two current entering in a particular point, no current is coming out. I mean current coming out is 0, right? I in plus I out equal to 0. This is I out, this is I in node, and this is 0. Okay. Or V out by V in equal to minus RA by RI. Am I right? Am I right, my son? Daughter? মেয়েদের মধ্যে থেকে কেউ বলো আমি ঠিক লিখেছি না ভুল লিখেছি?
Yes, sir. ঠিক আছে.
Then we can say the V output equal to V RF minus RE by into V in.
So মানে minus IN into RF.
Minus
I in, current in into RF.
into RF. No, I said V0 by V in equal to minus RF by RI. Now I am writing V0. What is V0 then?
V minus V in by RI into RF.
Right? Right or wrong? Tell me.
Yes, sir.
Yes, sir.
So now here you will find the output voltage will be multiplied with certain gain minus RF by RI into V. In open loop, what I have seen, output voltage equal to AD, or a gain, open loop gain, that is 10 to the power 5 or 10 to the power 6 into V difference up to voltage. Okay, that might be also V in, because one voltage is 0 and one voltage is V in. So VD equal to V in. Okay, so in open loop systems, the output voltage will have a highest gain like 10 to the power 6. So that's why due to 1 in microvolt input voltage, we will have a output voltage 10 volt. But in case of closed loop gain, systems, the output voltage is actually proportional, and proportional constant is minus RF by RI. or you can say the closed loop gain is minus Rf by Ri. Closed loop gain is minus Rf by Ri. Now you select yourself Rf. If your Rf is 10 volt, if your Ri is 1 volt, sorry, 10 Rf is 10k. 10k means 10 kilo ohm. If Ri is 1 kilo ohm, then what is the open loop gain? Closed loop gain?
10.
10, sir.
Huh? What is the closed loop gain?
10, sir.
Someone from ladies?
So 10, sir.
Very good. This is 10. So now look, earlier case we have a gain 10 to the power minus 6 in open loop mode. And in that case, we have a no control over the gain. We have a no control. And now in case of closed loop, we have a gain 10. And definitely we have a control over the gain because we can select RF and RI. We can also select RF and RI. If we select RF equal to 220 ohm, the famous resistance is 220 ohm and Ri is 100 ohm. Then what will be the gain?
2.2.
2.2, sir.
The gain will be
Sir, Ri is
2.2.
1000 or 100, sir, because you have written 1000.
RF is 220 ohm, Ri is
That is O.
100
That is
ohm.
O.
Oh,
That is ohm.
okay, sir.
So it is the 2.2.
2.2, sir.
The gain is 2.2. Look, that's really you can control the gain. Right now in closed loop operation, you can control the gain. So if your output voltage is 3 volt, you don't need to operate in open loop gain. If you operate in open loop gain, you will definitely get here minus 10 volt as it is given in a inverting terminal. Always the opposite, and this will be the saturated voltage according to the supplied voltage, VCC or VE. But if you apply here closed loop operation and you select 220 ohm in RF and Ri is 100 ohm, then the gain is 2.2, then output voltage will be what? 2.2 into 3. So that means 6.6 voltage will be the output. So that means you can measure that output. It is not like a saturation voltage 10 volt. So you have a control over the output voltage. That is benefit of the closed loop operation over the open loop operation. You always control the output gain. So this is inverting terminal. Similarly, you will find a non-inverting amplifier. Just hold on. My side is hanging. Okay. This is non-inverting amplifier. You may see the picture here. You have to apply where KCL. You have to apply the KCL
Summation point.
in this terminal. As this is 0, what will be the voltage here? Sorry, this is not 0. What will be voltage here? What will be voltage there? What is VD? What is VD?
The voltage difference.
Mohsin. Mohsin?
Yes, sir.
So can you answer this one? What is VD here?
No, sir.
Why not? What I discussed, why have you not asked me what is VD here? I told you the virtual ground, no? Now I
So
said
because for that we have to know the potential of the negative terminal.
now the potential here is a what? Directly V. So you are forcing here V. And we said the VD is remain zero, almost zero. So the voltage here is same. VD means difference of that voltage and that voltage is zero. So that means this is V in also. This is V in also. This voltage difference will remain zero due to high input impedance. So now the voltage current will be here coming out from this terminal to ground. Another current will be here output to input because output always high and input always low. Applying KCL here, Mansoor, Moisun, sorry, Maisin,
Yes, sir. I'm listening.
tell me that node analysis. What will be the current here? If this is output current, what is the output current? V out minus V in by R1.
R1.
This is entering here. What is the leaving current?
So V in by R2.
Very good. V in by R2. So they will be same.
Yes, sir, equal.
So V out by R1 minus V in by R1 equal to V in by R2. Or otherwise you can say V in by R1 plus V in by R2 equal to V out by V0. Right? Right?
Yes, sir.
So from there, that expression, what you will find? V out by R1 equal to V in by 1 by R1 okay. Then V0 by V in equal to 1 plus R1 by R2. This is here. Is it clear?
Yes, sir.
Yes, sir.
So the gain here is 1 plus R1 plus R2. That means in non-inverting operation, gain always more than 1. Gain is always more than 1. If you consider R1 R2 is same resistance, then the gain is 2. If you consider R1 R2 is same resistance, then gain is 2. Okay. If you consider R1 is 0, R1 is 0 means conducted, then that gain will be 1. Then that gain will be 1. That is called voltage follower. That is called voltage follower. Then whatever the input voltage, you will find the output voltage same. That is called voltage follower. Okay.
Yes, sir.
So this part is clear to you. Now here is some special kind of circuit. By name you can identify they are actually
filter, sir.
By name, band pass, low pass, high pass. What do you mean?
So the filter frequencies.
Very good. These are filter circuit. These are filter circuit. Look over the circuit. Prosenjit Mondol. Prosenjit Mondol. Prosenjit Mondol.
Yes, sir.
Can you see a high pass filter?
Yes, sir.
Can you see a high pass filter? তো ফুল গাছটা দেখবে ওটা পুড়ে যেতে পারে তো ফুল গাছ ঠিক আছে তো ওটা ডালটা ভেঙে গেছিল তো can you see a high pass filter?
Yes. Sir,
Low
sir.
pass filter, band pass filter. And band
Yes.
pass filter, what can you understand? Which part is low pass here? Which part is high pass here?
Sir, it's sir আসলে ফোনে করছি তো একটু ছোট দেখ
Sir, left এরটা high pass, right এরটা low pass.
হ্যাঁ কি হয়েছে
Sir, left এরটা high
এটা
pass,
high pass.
right এরটা low pass.
দেখতে পাচ্ছ না হ্যাঁ
হ্যাঁ স্যার স্যার আসলে স্যার হ্যাঁ স্যার এবার দেখতে পাচ্ছি আসলে ফোনে করছি তো
মনে করছো চলো ঘরে কম্পিউটার নেই নাকি না
হ্যাঁ,
তুমি
স্যার।
বাইরে ঘুরছো
না স্যার বাড়িতেই আছে স্যার
তাহলে ঘরে কম্পিউটার নেই
হ্যাঁ স্যার আসলে ওয়াইফাইটা নেই স্যার ফোনের নেট দিয়ে করছি তো তাই জন্য ফোনেই করছি
তো ফোনে হটস্পট করে না
হ্যাঁ আসলে স্যার এখানে ইন্টারনেট স্পিডটা কম আমি আপনাকে বললাম না সেই একটু প্রবলেম
কোথায় তোমার বাড়ি কোথায়
স্যার একদম এয়ারপোর্টের এখানে স্যার একদম এয়ারপোর্ট 1 নম্বর এখানে স্যার
ওখানটায় ইন্টারনেটে তাহলে এরোপ্লেন চলছে কি করে
না স্যার এখানে বিশাল প্রবলেম মানে খুবই প্রবলেম হয় আপনি মানে কিছু জিনিস মানে ভিডিওস বা কিছু ধরুন ক্লাস রেকর্ডিং ওইগুলো ডাউনলোড করতে মানে বিশাল স্লো ডাউনলোড মানে 0 kbps মানে
টিকা সাহা টিকা সাহা
Yes, sir.
can you listen me
Yes.
so have you seen that picture here your internet is working well na
Yes, sir. Will.
so this is high pass filter constructed with what op-amp and resistance and capacitors look
Yes.
here resistance and capacitor connections and this is low pass filter you all please look on that picture this is all you this is another configurations where you see that R and C position are swapped in high pass filter wherever C and R you just look over this one and low pass filter R and C are swapped am I right
Yes, sir.
and in case of band pass filter there is a one high pass filter and low pass filter can you say me which one is the high pass filter which one is low pass filter
Sir, left এরটা high pass, right এরটা low pass.
huh
Left at
What?
high pass, right at
what is this one
Sir, high pass.
high pass,
what is this one
low pass,
who have said name who said this one huh
Sir, Mustafa.
Mustafa now Mustafa check it out this is you said high pass you are right this is high pass configuration so how can you change see How can you see the resistance position and this resistance position, and even in this resistance also. And it is low pass, this resistance, and this resistance. So this is low pass filter, this is high pass filter. Combinedly, they construct band pass filter. Band pass filter means a particular band will be allowed. A frequency will be plotted this way, and amplitude will be here. Then you will find that frequency low, FL, and frequency high, upper. Within what the signal will be considered and rest of the signal are not considered. That is called band pass filter. Okay, this is also done by that filter system. What is the low pass filter? If we draw a frequency versus amplitude graph, amplitude here, frequency here, then for low pass filter, there will be definitely a frequency, and that frequency will be called FL or FU for low pass filter.
So it will
AFL.
not allow the high frequencies.
Now, let me know first one. My question is that in low pass filter, there was a standard AF which we have to mention. What is that?
FL.
FL or FU?
FL.
No, this is FU, upper cutoff frequency. Upper cutoff frequency. That means the frequency we allow within that range. This is called upper cutoff frequency, FU. This is called lower cutoff frequency. Lower cutoff frequency. This is called upper cutoff frequency. And for high pass filter, definitely this will be
FL, lower cutoff frequency.
this will be FL. FL, and onwards the frequency will be allowed. The signal will be here allowed, and this signal will not be allowed. And low pass, the signal will be allowed, this one will not be allowed. After lower upper cutoff, no signal will be allowed to pass through the circuit. So if you put any signals more than of that upper cutoff frequency, it will give you zero output. But in case any signal below the lower cutoff frequency, then that signal will be zero. Okay. But in case of band pass filter, within this lower cutoff, within this higher cutoff, the all frequency signals will be allowed. So this is the range. This is the range of frequency. Range of frequency will be allowed. Or you can say there will be a band pass. Bandwidth. There will be a bandwidth. That bandwidth means delta F, which is FU minus FL. Within what frequency will be allowed. Okay, this is another circuit of filter circuits. Now come to our basic part from where we came here. So this was our electro dynamometer. Electro dynamometer means where the rotor is forced to rotate in a magnetic field. Where rotor is moving or rotating in a magnetic field, and due to what the magnetic field actually cause a current inside the current or through the coil, current through the coil or the wire, which actually wound up on the coil. So that current actually fed to amplifier and integrator, then to CR to monitor how much current is produced. Okay. I started with this one by de-arsenable galvanometer, but that is just opposite. This picture actually electro sometimes called Electro Dynamometer, or sometimes called electrodynamic type displacement measuring instrument. Electrodynamic type displacement measuring instrument. How the displacement will be measured, I am coming to that point. Sometimes called electrodynamic type displacement measurement system instrument. What I said the name?
Electrodynamic type displacement measuring instrument.
Very good. Who said? Sudasutto?
Yes, sir.
Your voice is quite familiar now. Whoever will communicate with me will be close to the teacher. I don't mean me. Whoever in your class communicate with the teachers will be close to the teachers. Like Sudasutto is communicating, the parameter, I mean caller voice is now familiar to me. So similar way, I will encourage you all to communicate in the class with all teachers, as if you should be recognized by teacher by your voice, by your behavior, by your attitude, whatever. So always keep a positive attitude, always keep communications with the teacher, class teacher, whoever the class teachers. You need to know or need to be familiar to the teachers. If you are not going to be familiar yourselves to the teachers, to the friends, that means you have some kind of negative attitude. Or you are introvert, or you are not a communicatable person, or you might have some kind of low confidence. We usually consider this way. The student. So be better, communicate with the teacher. Be better communicate. As I am asking some questions, I am not looking over who is speaking there. Sometimes I used to come back to the Google Meet page, but normally I used to look over the Microsoft Word page, workbook, Blackboard or whiteboard page. So I don't know who is speaking there. Now the voice of Sudasutto is clear, and the lady is Silpa. Am I right, Silpa or Sitoma? Who was speaking earlier?
Sir, Anindita, sir.
Huh?
Anindita, sir.
Anindita, sorry, Anindita. Your voice was quite familiar to me, Anindita. And definitely Joydeep's voice is familiar, Mohisen's voice is familiar. Today we are in an online class, so you should be known by your voice, not necessarily by your face, because I am not seeing you regularly, I am looking over the whiteboard. So your voice means this is the only way you can communicate, you can be recognized by your teacher. So you just communicate with your teacher. I am advising you all. Okay. Earlier your face was moving, when you are moving in the building or departmental building, you may be recognized by your face, whatever it is, or your behavior. But today, whatever your behavior, whatever your attitude, whatever your face is simply your voice. So you better communicate with your voice, as we can understand whoever is speaking is there. And your examination is going to be conducted by continuous assessment. Internal evolutions. So your assessment will be done easily. If you're not communicating, you will get a minimum marks. You may be a good student, but there is no other options in online mode. There might be some chances to recognize you, but you just communicate. Otherwise, we will consider the student have a low confidence. Student is not communicating at all, or the student is less interested in the class, or student is doing whatever but not doing the class, just simply logged in. So it is always better that you are active in mode by communicating with your teacher. It is my strict advice to you all to do this one with your class teacher and make it habit. Make it habit. In every class, you make it habit. You will be benefited at the end of your years, at the end of your semester. Okay. Now come to the point. So we have explained this is electrodynamic type displacement measurement. Earlier I said electrodynamometer or electrodynamic type displacement measurement. Simple structure is that suppose that wheels here it's moving from particular angle theta. This is angular displacement from this position to from this position with the velocity v. Due to that velocity, there will be some current I, small current that I fed to that to the system. Definitely there will be resistance system, and finally it produces a graph over the oscilloscope. The whole system is a block diagram in this way. Motions, the motion is detected, Vx is detected, input variables, coil and magnet is there, is transducing file, elimination, transducing eliminator, transducing element, and next is amplifier or integrator. Hello? কি বলছেন? আচ্ছা আচ্ছা বলুন। ও আমি পাঠিয়ে দিচ্ছি, এখন ক্লাস নিচ্ছি, পাঠিয়ে দিচ্ছি। এপিটি অফিসে পাঠিয়ে দেবো। হ্যাঁ হ্যাঁ, আমি একটু ক্লাসটা নিয়ে নিই। হ্যাঁ হ্যাঁ, ওকে। আমি ম্যাথস ডিপার্টমেন্টে পাঠিয়ে দিয়েছি অলরেডি। আচ্ছা আচ্ছা, ঠিক আছে। ওকে ওকে ওকে, বুঝতে পেরেছি, ঠিক আছে। So here, what I said that there is another part, amplifier integrator. Now tell me, what is the integrator? Integrator means, suppose e to the power st. What should be the integrated value e to the power st?
E raised for st upon s.
Huh?
E raised for st upon s.
Is it?
Plus C, sir.
Plus integration constant.
Am I right? Somebody?
Yes, sir.
Who is speaking?
Sir, Anindita.
Anindita, okay. Is it your okay, Anindita?
Yes, sir. E to the power st upon s plus the integration constant.
So if f equal to e to the power st, then integrated value is f by s. I am considering c is 0. So e to the power st is the signal, then f by s will be the integrator output. I mean, I put that ft to a integrator. So e to the power st was a signal enter in a integrator and output is e to the power st by s. Okay, so e to the power st যদি input signal হয় s, input signal integrator তাহলে সেম ইনপুট সিগন্যাল থাকবে, শুধু নিচে একটা এস টার্ম আসবে, তাই তো?
Yes, sir.
So if we talk about the differentiator, the same thing will be happen. Signal will be input, differentiator will be there, and the output will be s into a signal. The s will come out from the signal. What is s? S actually component of frequency. S is actually component of frequency. Look, if S is omega, then the signal divided by the value of omega. In case of integrator,
Yes,
if
sir.
S is omega, then signal is divided by omega. Now you increase the omega. What will be the value of output of integrator? It's getting lower. So when S is increasing, then whole functions will be decreasing. Am I right or wrong?
Yes, sir.
Yes, sir.
S is increasing means whole fraction is decreasing. That's when the systems, integrator systems, is like a systems where the higher frequency signal will die out, where the higher frequency signal will die out. Integrator is such a system where the higher frequency signal will die out. In case of differentiator, what we will find? The differentiator, the signal will be multiplied with the frequency component. Signal is multiplied with the frequency component if S is omega. Okay, then we can say signal differentiator S into signal. Now I said S equal to J omega. Omega is angular frequency. Now look over the integrator. So in case of integrator where the frequency omega is increasing, that means the output of the integrator is decreasing, or higher frequency signal will die out through when it is come through, or when it passes through the integrator. If it is a differentiator, then higher frequency signal will be allowed. If the signal is a lower frequency signal, definitely S is smaller means the output of the differentiator will be smaller. Suppose S is fraction 0.1, then the output of the differentiator will be multiplied with the 0.1. It means it will be 1/10 of this one. So lower frequency signal will die out, but in differentiator, in case of integrator, higher frequency signal will be die out. Now tell me, what is the behavior then? That behavior of integrator will give you will help you to remember which things.
So low frequency.
It's a low pass filter.
Low pass filter, very good. That means what we studied just few minutes before, integrator behave like a low pass filter. Low signal will be allowed. If it is a differentiator, then high pass filter. Okay, so this is the active filter. Active filter is allowed, applied, and then the signal come out from the signal conditioning part. Now this is displaying part. This is the data displaying part or signal displaying part, means a output device, cathode ray oscilloscope, which actually give you output of the voltage signal. Now what you have to do? You have to consider that voltage in terms of what? You have to scale the voltage in terms of what? In terms of motion or displacement. In terms of motion or displacement. In terms of motion or displacement. If x is the displacement, then dx by dt will be the velocity. If you're going to consider velocity component, then the you have to scale the voltage signal with respect to velocity. If you consider simple a displacement, then 1 centimeter displacement or 1 degree centigrade, 1 minute or 1 second angular displacement, you will find different output voltage. According to what you have to scale down. This is another instrument which I discussed, is called electrodynamic type displacement or velocity measurement devices, which actually opposite of galvanometer. In case of galvanometer, what happened? Magnetic field and electric field will be provided due to what torque developed, and that torque actually produce a particular displacement. And that kind of galvanometer can be connected here. That kind of galvanometer can be connected here to know the relation with the X with voltage, or X dot with voltage, or even X double dot means acceleration into voltage. That can be measured by galvanometer. Galvanometer means opposite behavior of the electrodynamic or dynamometer. Okay, this is all about of the instrumentation part which I started. No, it is all about which first chapter which I actually started. I don't want to discuss more about the individual instrument. Rather, I will come to or jump to next part, which is basically static characteristic of transducer. So I want to mention some points. You keep in your mind. Or should I give you a? Just hold on. Rajdeep Kundu,
Yes, sir.
can you read the first point here?
The transducer element should recognize and sense the desired input signal and should be insensitive to other signals present simultaneously in the measurand. For example, velocity transducer should sense the instantaneous velocity and should be insensitive to the local pressure or temperature.
Is it clear?
Yes.
So what I said earlier, the transducer measuring a particular parameter, like I have given an example and discussed the block diagram where the velocity or the displacement or the acceleration can be converted in electrical output. Now we can say there will be desirable characteristic of transducer, that the transducer element should recognize and sense the desired input signal. Desired input signal means what? Desired input signal means that particular physical parameter which you are going to measure here, not the other parameters, and should be insensitive to the other signal. That is simple. When a body is rotating, means it's developing a torque, it's giving a stress or giving a force, whatever. But you are not going to measure force. Or if you are going to be concentrated on the velocity measurement, definitely your systems will not focus on the acceleration, will not focus on the pressure or stress or torque. So that's why it's a dedicated system. So it means a dedicated system. Okay. Number two, what it is said, Subhajit Mandal. Subhajit Mandal. What is number two? Can you read it out loudly? It should not alter the event to be measured. What does it mean?
The input signal should not be changed.
Input signal, not only the input signal, the signals of the system, signal of the system should not be changed. One thing you have to remember, you may study the thermometer. Okay, you have studied the thermometer, you want to measure a temperature. You inserted body temperature of a particular your brother or sisters or whatever. So once you put your thermometer under arm to measure the body temperature of your brother, suddenly it's not stable. You pick it out that thermometer and put in your underarm. Will it give you the results?
No, sir.
No, sir.
It's erroneous process of measurement. It's erroneous process of measurement. Okay, so it should not alter the events. Once you are going to measure a particular parameter of a particular system, it cannot change the system or cannot change the parameter. If you are going to change the system, you have to recalibrate. The term is recalibration. Recalibrate your systems or recalibrate your measuring device with respect to the new systems or new event. Without calibration, you want to change your event, your result will be wrong. So that's why the desirable phenomena of measure transducer element, it should not alter the event to be measured. Or one thing more, the system you may consider look like here. You are going to measure temperature sensor. As I have given example. So temperature can be sensed by your thermocouple also, can be sensed by a thermometer also, can be sensed by a resistance also. That means RTD, resistance temperature thermometer. Now you inserted RTD. So RTD will sense the temperature which happens in environment, right? Which happens in environment, right? Now your RTD itself is heating up the environment. Is it good to measure the temperature?
No, sir.
Definitely it's not, because the transducing element is altering the environment. Transducing element is also altering the environment. You want to measure the boiling point of water right now is 60 degrees centigrade. That's why I inserted a metal thermometer. If metal itself is heating up, it will rise up the temperature of the water, no? Then how can it be possible to give you a better measurement? So that means transducer element should not alter the events which will be measured. Okay. Number 3. Saurabh Sen, can you read it out?
Yes, sir. The output should preferably be electrical to obtain the advantages of modern computing and display devices.
Output again, please repeat.
So the output should preferably be electrical to obtain the advantages of modern computing and display devices.
Should I explain it? Should I explain it? Is it new things to know?
No, sir.
Very good. What will be the next point? Surya Datta, what is the next point? Udbhas,
Yes, sir.
what is the next point?
It should have good accuracy.
Now, Udbhas, you just read out for next point also. Next 2 or 3 points also.
Then the fifth point is it should have good reproducibility, that is precision. And the sixth point is okay. And the sixth point is it should have amplitude linearity.
And next point.
The seventh point is it should have adequate frequency response, that is good dynamic response.
So the next points are mainly related with the some basic characteristics. Basic characteristics, the term is like accuracy, reproducibility, linearity, and dynamic characteristics like frequency response. Some are static characteristics, that is those are the accuracy, reproducibility. Some are dynamic like frequency response, like phase distortions, like acceptable limit of the accuracy, and so those are the dynamic and static characteristics. We will discuss this thing in next class in details. Then after you can realize what are the desirable characteristics of a transducer. What are the desirable characteristics of a transducer? Okay, that's enough for today. I'm taking your attendance.